everybody, welcome to today's lesson. Today we're going to be starting our new unit, which is going to be all about covalent bonding. So we've taken the beginning of this bonding unit, which is really quite a large unit, and we've spent that talking all about ionic bonding. So I do want to start there just to kind of refresh our minds and talk a little bit about ionic bonding. So an ionic bond, okay, an ionic bond, for those of us that don't remember, is going to be a bond between a metal and a non-metal. Okay, a metal and a non-metal, and it involves the transfer of electrons, meaning, okay, the metal is going to donate its electron to the non-metal. So I want us to kind of review and really think about, why is that the case? Why does the metal donate its electron to the non-metal? And so in order to talk about that, we have to again think back to our previous unit on periodic table. So the metal, if we think of metals in terms of electronegativity and ionization energy, remember that metals have low ionization energy and they have a low electronegativity. And that means that it requires very little energy to remove. So very little energy to remove those electrons from the metal. And they have very little attraction to new electrons. Okay, and so what that means is that it's easy for the metal to lose its electron, and the non-metal, let's talk about that next. Okay, our non-metal is going to have, and I'm going to do this in yellow over here, our non-metal has very high ionization energy and very high electronegativity, meaning they don't want to give their electrons away. It requires a lot of energy. It's not favorable. Okay, requires too much energy. Okay, and to remove the electron, and they have a high attraction to electrons, so it's easier for them to gain electrons. So if we look at this, then what results from this is like for example with sodium chloride, our Na, which is our metal, donates its electron to our chlorine or our non-metal, and we get the resulting Na plus and Cl minus. Okay, and they attract based on their charge, hence the ionic bond formed by two ions that are charged, and they stick together. And so this, again, is our Lewis dot diagram of an ionic bond. But what I want to focus on today is not ionic bonds. I want to focus on now what's called a covalent bond. And so my question is then, why would two nonmetals not form an ionic bond? So a metal and a nonmetal form something that's called an ionic bond. Why do two nonmetals not form an ionic bond? So I do want to just go ahead and start with just an example. So let's take the example H and Cl. Okay, hydrogen and chlorine. Both of these are considered nonmetals. Okay, and so we have to think about, in terms of ionization energy and electronegativity, what's going to happen. So hydrogen has 1 valence electron, chlorine has 7 valence electrons. So you might be thinking, well, shouldn't hydrogen just donate its electron to chlorine? That's what sodium does. Chlorine would be satisfied, hydrogen would be satisfied. But our problem is that hydrogen and chlorine, both being nonmetals, they both have high ionization energies and high electronegativities. And so neither of them want to give away their electron, and they both have a decently high attraction for electrons. So what do we do if hydrogen doesn't want to give away its electron and chlorine doesn't want to give away its electron? How can we satisfy their octet rule? How can we make them stable? And so what ends up happening is they form what's called a covalent bond. And our covalent bond, let's go ahead and define that. Okay, our covalent bond is a bond formed between two nonmetals where electrons are shared. So now, instead of donating an electron, our electrons are being shared. Hydrogen says, I'll give you a little bit of mine. Chlorine says, I'll give you a little bit of mine. And together we can make a pair of electrons that we can share, and we'll both be satisfied. So let's go ahead and talk about what that covalent bond looks like. So I'm going to go ahead and I'm going to just scroll down to get a little more space here. And I'm going to still stick with that hydrogen chlorine example just because it's really simple. So again, we have our hydrogen, okay, with its 1 valence electron. We have chlorine with its 7 valence electrons. And we need to form a covalent bond between the two so that they're both satisfied. So in order to form that covalent bond, we're going to go ahead and share this pair of electrons that are currently unpaired. And to represent that as a drawing, okay, we would end up with HCl with its still 6 electrons here, but now that pair that they share is represented as a line, okay? And so I want to take a moment to talk a little bit about looking at this, what this truly means, okay? So first and foremost, let's talk a little bit about what's called a lone pair. So this set of electrons right here is called a lone pair. And a lone pair is going to be a pair of electrons, okay, a pair of electrons that are not involved in the bond at all, okay? So chlorine already had 3 lone pairs to start, but it had 1 unpaired electron. And that 1 unpaired electron became part of what we call our bonding pair, okay? So our bonding pair is in red. And we call this our bonding pair. And what's notable about it is that it represents 2 electrons. Okay, each line represents 2 electrons that are shared between the hydrogen and the chlorine. Okay. Now, this bonding pair, so anytime you look at this, and anytime I draw a Lewis structure, and again, this is now called a Lewis structure, just like we had seen for our ionic bond up here, and they're very different, but this Lewis structure, anytime I look at it, I have to ask myself at the end, you know, I go back and check, is everybody satisfied? Is every atom satisfied? And the way that we have to do that is we have to think of how many electrons does each of those atoms want, okay? So hydrogen, okay, with its 1 valence electron needs, remember, it's one of our exceptions to the octet rule. It only needs 2 electrons total. So it's going to form only 1 bond because it needs only 2 electrons, okay? Chlorine, on the other hand, had 7 valence electrons. And it also only needs 1 bond because it's going to have a maximum of 8 electrons. So as I'm checking my Lewis structure at the end, this line, since it's touching hydrogen, represents the fact that hydrogen now has 2 electrons and it's satisfied. The line also represents that chlorine has 2 electrons on this side of it, and it has 2, 4, 6, and 8, and is also satisfied. So since they are able to share, both of them have now fulfilled their octet rule and they are considered stable. So let's go ahead and take a look at a couple more of examples and how we would go through drawing those Lewis structures. So if you're following along on my guided notes sheet, I have them written there for you, but I want to go ahead and take a look at the structures of CH4, NH3, and H2O. And anytime that I'm asked to draw the Lewis structure or show the covalent bonding process, I always take time to figure out which of these atoms in my formula is considered my central atom. How do I know which atom goes in the middle of my Lewis structure? So in order to do that, I draw out their atoms, or I draw out the atoms individually, okay? And I figure out how many bonds can each form, or how many bonds does each need to form in order to satisfy the octet rule. So let's go ahead and start with CH4. So carbon, in class thus far, I taught you guys that our electron dot filling for these atoms is pair the top two and then go around clockwise and loop back around clockwise for all 8 electrons. Carbon is your one exception to the rule. Okay, carbon is special. It belongs to group 14 and it undergoes a process called hybridization. Now, I'm not going to dig too deep into that because that's not really content that we need for this course specifically. If you're interested in it, I'd recommend looking into it. But that process of hybridization allows where carbon would normally look like this, it allows it to unpair this electron and place it on the side. So now carbon has 4 places to bond. Because carbon has 4 electrons only, and it wants a total of 8 electrons, and therefore it needs 4 places that it can form a bond. So carbon now has 1 electron on each side, and I mark underneath and I note that it's going to form 4 bonds total in order to satisfy the octet rule. Hydrogen, again, is just the example, or it's one of the exceptions. So it needs a total of 2 electrons. It has 1, which means it's only going to form 1 bond total. Okay? So to determine which of these is going to go in the center, your central atom is going to be the atom that requires the most bonds. Okay? So it's going to be our atom that requires the most bonds. So carbon is going to be our central atom, meaning it's going to go in the center of my molecule because it requires the most bonds. Notice too that I have 4 hydrogens total. So when we are doing this, and I'll demonstrate it over here and then put the finished product over in the blank space, but I have 4 total hydrogens. Okay, each of those hydrogens is going to share with your carbon, okay? And we are going to form 4 total bonds. 4 hydrogens, each needs 1 bond. Carbon needs 4 bonds. And our final product is going to look like this, okay? C, H, 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 and H, okay? I go back in, as I mentioned before, and I just double check that everybody is satisfied. So carbon needs a total of 8 electrons touching it. Remember that each of these lines is 2 electrons, 2 electrons, 2 electrons, and 2 electrons. So carbon does have a total of 8 electrons, and each hydrogen has 2 electrons. Everybody is satisfied. Let's talk about NH3 next, okay? So NH3, we have, again, N, which has 5 valence electrons, and H, which has 1 valence electron. If nitrogen has a total of 5 valence electrons but needs 8 electrons, it's going to form a total of 3 bonds, and H is going to form 1 bond each, okay? And we have 3 of them. You can kind of see where this is going. So what we're going to do then is we're going to say, well, if this is the case, then my central bonding atom is going to be nitrogen, right? This is our center atom. And then my 3 H's that I have are going to bond with that N. So again, let's go ahead and draw that out. So we have N with its 5 electrons. I have an H, I have an H, I have an H, and each of those is going to share their pairs of electrons until we are satisfied. And we're going to end up with N with a lone pair up top, H, H, and H, okay, as our final answer. And again, you go back through and you do your circular check. 2 electrons here, 2 electrons here, 2 electrons here, and nitrogen has the lone pair, which again is 2 electrons. So nitrogen has 8 electrons, which is where it wants to be, and each hydrogen has 2 electrons, okay? Last but not least, let's look at water. Now, this is where, and you'll notice that these structures were very easy. There wasn't really any option of where to stick things. There was only, you know, the places that were empty. And when I taught you guys this X with all of the different numerical values, I had told you that it was really important that we follow that rule, because when we start to draw these Lewis structures, looking at that is going to be very important. And it's really the case for primarily for things like water. Oxygen, remember, pairs the first 2, then we loop around 3, 4, 5, and 6. And you'll notice that it left just these 2 empty spaces, one to the left and one to the bottom, and that's where our bonds will go. And we'll talk more about that when we talk about the shapes of these molecules. But if you were to do something like this and leave the unbonded pair or the unbonded electrons to the left and to the right, that would be incorrect. So again, that X with all of the values going around it, that's a really important rule to follow. So here we go. We have oxygen. Oxygen has 6 valence electrons and H has 1. Oxygen needs to form a total of 2 bonds in order to satisfy the octet rule, and H needs 1 bond, okay? So we're going to go ahead and we're going to put our values down here. So we've got our O, and we have an H, and we have an H. And we're going to go ahead and pair those off. Okay, so we form a bond here, and we form a bond here. And we end up with our final answer for water, which is this for our structure. And again, we go back in and we loop and do our electron check. So 2 electrons, 2 electrons. Each hydrogen is satisfied, and oxygen has these lone pairs off to the side. So we have a total of 8 electrons going around. Okay, so this is the idea of drawing Lewis structures, but I do not want you guys to get confused, because this is considered a Lewis structure for a covalent molecule, and this up here was a Lewis structure for an ionic compound. And it's one of the biggest issues that I have each year, where students forget to double check, is this ionic, is it covalent, and then make sure they're drawing the appropriate Lewis structure. Okay, so those are our Lewis structures. What I want to go ahead and do, though, is I want to just give you a step-by-step process for how we just did this, just so you have a rule written down. So here's our step-by-step process for drawing those Lewis structures. Okay, so step 1, when we're completing this, is we're going to determine the central atom. And remember, your central atom is going to be the one that requires the most bonds. Okay. Step 2, we're going to attach and circle all atoms until the octets are fulfilled. And then step 3, there's 2 different checks that we're going to do, okay? So the 2 different checks, we'll do 3A and 3B. 3A, check all octets. And I want to point a secondary check to you, okay, which I didn't go over up here, but I'm going to go back and do, is that any atom which starts with lone pairs ends with that same number of lone pairs. Okay, so what do I mean by that? Well, if we look back up to, let's say, CH4, your initial or your central atom carbon started with 0 lone pairs, right? It just had 4 unpaired electrons, and therefore it will end with 0 lone pairs. So if we look at our final answer here, you'll notice that there were no lone pairs on the carbon. Hydrogen also started with 0 lone pairs, and it ends with 0 lone pairs. Nitrogen, on the other hand, over here, our nitrogen started with 1 lone pair, and notice that at the end, it ends with 1 lone pair. Okay, hydrogen still had none. Oxygen over here started with 2 lone pairs, and it ends with 2 lone pairs. I'm going to decide to stop this video and pause here. In class tomorrow, we're going to talk a little bit about double and triple bonds. So please be ready to take notes in class tomorrow, just at the beginning, and then we're going to do a bunch of practice. All right, thanks so much, guys. Have a great rest of your day.